In this lecture, we are going to discuss about universal logic gates. We have two universal logic gates, NAND gate and NOR gate. So in this lecture, we are going to have the logic gate designing using only NOR gates. So we know that total we have 7 logic gates: AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate. And these are the logical symbols of all the gates. Like here we have the symbol of AND gate. A and B are input and P is the output. This is the logical symbol of OR gate. A and B are the input and R is the output here. This is the logical symbol of NOT gate. Input here is A and the output here is V. This is the logical symbol of NAND gate. Input here is A and B and output here is Q, and Q and P are complementary. Q is the output of NAND gate and P is the output of AND gate. Both are complementary. This is the logical symbol of NOR gate, where A and B are inputs and S is the output. Now we have S is the output of NOR gate and R is the output of OR gate. So these two are also complementary. This is the logical symbol of XOR gate. Here A and B are two inputs and T is the output. And this is the logical symbol of XNOR gate, where A and B are inputs and U is the output. Now what is the relation between T and U? T and U both are complementary. So this is the summary of truth table of logic gates. So we have drawn a common truth table having all the logic gates. Like A and B, we are taking two input variables common to all the logic gates. Now this P is the output of AND gate. We can see here. Q is the output of NAND gate. Here a NAND gate is shown with the Q output. R is the output of OR gate. This is the R output of OR gate. Then S is the output of NOR gate. Then we have T. T is the output of XOR gate. And U is the output of XNOR gate. So we can see for the various combinations of A and B, like we have 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. We can see what is output P, Q, R, S, T and U. So how we define a universal logic gate? Basically, a universal logic gate is a gate which stand alone or in a group can implement any of the big Boolean function, any of the complex Boolean function without using any other logic gate. So with the help of universal logic gate, we can construct all the other logic gates. So we have two universal logic gates, that is NAND gate and NOR gate. That means with the help of NAND gate, we can construct the other 6 logic gates, and same we can do with the NOR gate. So by using only NAND gates, we can construct all the 6 logic gates, and by using only NOR, we can construct all the other 6 logic gates. So NAND and the NOR gates, they are most widely used in all the digital circuits. Why? Because they are economical and easier to fabricate. So here we are designing all the logic gates using only NOR gate. So quick review about NOR gate. This is the logical symbol of NOR gate, where A and B are two inputs and S is the output of NOR gate. And this is the Boolean expression of NOR gate. In this Boolean expression, we have output S, that is equal to A plus B to the whole complement. And this is the truth table of NOR gate, where A and B can have total 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. So S is the output of NOR gate, and for 0, 0 combination of input, S will be 1, and for rest 3 combinations, S will be 0. So what is the conclusion in the NOR gate? That if all the inputs are 0, then only the output is 1. And if any of the input becomes 1 or all the inputs becomes 1, output will be 0. So first we design inverter using only NOR gate. So this is a symbol of NOR gate. We know that in the NOR gate we need minimum 2 inputs. But for the inverter, that is the exceptional case that works on a single input. So what we do, we take NOR gate and we short both the inputs, that is A and B, and provide here a common input signal, that is A. So that means A signal is provided to A input of NOR gate as well as B input of NOR gate. So A and B inputs are driven by a common input signal, that is A. So how to see the output of this NOR gate acting as inverter? What is the output of this NOR gate? The output we are taking as V, and V can be written as A plus A to the whole complement, because the general expression is A plus B to the whole complement, and B is also A here because both are driven by common signal. So here V will be A plus A to the whole complement, and A plus A in the digital electronics we know that is A. As per the OR law we have discussed, A plus A is A. So that becomes A complement, and A complement, that is the Boolean expression of inverter. Then next we have NOR gate as an OR gate. That means how to design OR gate using only NOR gate. So here we have the NOR gate with the two inputs A and B, and the output of this NOR gate will be A plus B to the whole complement. And if we pass this particular output via inverter, so that is taking complement of this expression, it is already complemented, so it will be again complemented, and complement to the complement will cancel out, and output we get here, that is A plus B. So this NOR gate we are using as an inverter, that we have seen in the last slide, that we combine the two inputs, we short the two inputs and provide here a common signal. So this is a signal that we are providing here, and that is taking complement of this signal. So output for the OR gate we are taking is R, and R is equal to complement of this signal. So here we have A plus B to the complement, and complement to the complement, that gets cancelled out, and output we obtain here is A plus B, and A plus B is the output of OR gate. So we have proved that this particular circuit is working as an OR gate, and that we have constructed using only NOR gates. Then next we have NOR gate as an AND gate. So here we design AND gate using only NOR gates. So here we have taken this NOR gate and pass here the input A. So this NOR gate is acting as inverter. We can see here A and B are shorted together and provided with a common signal A. So this particular NOR gate is acting as an inverter and inverting the signal A. So here we get A complement. Same way, this is the another NOR gate acting as inverter, but here the input signal is B. So this particular inverter is complementing signal B. So here we get B complement. Now A complement and B complement we pass through a NOR gate. So NOR gate, what it is doing? It is doing the operation one input plus another input to the whole complement, and the P we are taking as output of AND gate. So P is equal to one input A complement plus another input, that is B complement, to the whole complement, and this is of the form complement of sum. So we can apply here De Morgan's theorem. Complement of sum is equal to product of individual complements. So this becomes A complement to the complement dot B complement to the complement, and complement to the complement will get cancelled out. Here we have A dot and here we have B. So A dot B is the Boolean expression of AND gate. So we have verified that this designed circuit is working as an AND gate. So if we can design AND gate, so it is very easy to design NAND gate. So here this particular part of the circuit, this is working as an AND gate. In the last slide we have seen one inverter, we pass the signal A, it is giving A complement. Another inverter, we pass the signal B, it is giving B complement, and A complement and B complement we pass through the NOR gate, that is giving A dot B. But for the NAND gate, the expression is A dot B to the whole complement. So for taking complement of this expression, we are using one more NOR gate, and that is acting as an inverter. So this is inverting this signal A dot B, and here we have Q is equal to A dot B to the complement. So Q is the output of NAND gate we are taking, and the Boolean expression we are getting is A dot B to the whole complement. So we have proved that this particular circuit using only NOR gates is acting as NAND gate. Then next we have XNOR gate using only NOR gates. So here we have taken one NOR gate. So output here is A plus B to the complement. So this output we are passing through two more NOR gates, and the another input to the two NOR gates, here we are passing A and here we are passing B. So what is the output of this NOR gate? That is one input plus another input to the whole complement. And what is the output of this NOR gate? One input plus another input to the whole complement. So here we get the form, that is complement of sum, that is equal to product of individual complements. So here we get A complement dot A plus B to the complement, and that will be A plus B. So when we solve this, A bar A becomes 0, and here we have A bar B, and same way we get here AB bar. So finally we are putting one more NOR gate, that is taking the expression, that is one input A complement B plus another input, that is AB complement to the whole complement. So here we have the form, that is complement of sum, that is equal to product of individual complements. So one input is A complement B, we are taking complement of this. Another is AB complement, so we are taking complement of this, and remove the plus sign and add the and sign here. So we have complement of sum is equal to product of individual complements as per the De Morgan's theorem. So again we can apply here the De Morgan's theorem, that is complement of product, that is equal to sum of individual complements. Here also we apply De Morgan's theorem, the complement of product, that is equal to sum of individual complements, and finally we solve it by multiplying A with A complement, that is 0, then multiply A with B, we have AB, then B complement is multiplied by A complement, we have A complement B complement, and B complement B becomes 0. So finally we have the expression AB plus A complement B complement, and the output variable we are taking is U as the output of XNOR gate. So this is the Boolean expression of XNOR gate. So we have verified that this particular circuit is acting as an XNOR gate, and that we have constructed using only NOR gates. So if we can design the XNOR gate, then designing the XOR gate is very simple. Just we have to add one more NOR gate, that is acting as an inverter. So in the last slide, this is a circuit diagram we have seen for the XNOR gate using only 4 NOR gates. So with the 4 NOR gates we have designed XNOR gate, and here we have added one more NOR gate acting as an inverter. So that is inverting this expression. So what is the complement of XNOR? That is the XOR. So we can solve this expression and verify that if we take the complement of this, so complement to the complement will cancel out, and finally we get the result here A complement B plus AB complement, and that we are putting with the output, that is D. So T is the output of XOR gate we are taking, and that is equal to the Boolean expression of XOR gate. So in this way we have verified that this particular circuit is acting as an XOR gate using only NOR gates. These are the references I have used. Thank you.